So where we ended was looking at the interactions between any two atoms. Right? And we said that those interactions become important because those things dictate a whole bunch of physical properties. Right? For the sake of this class, the physical properties that you need to be concerned about, right, would be your phase, oh man, I'm just going to erase all that. Your phase transitions, solubility, and vapor pressure. Right? So to be able to use those, what we have to be able to do is to have some understanding of what's going on with our bonds and forces and how that applies outwards. Which of those do you feel would be the easiest to interpret? The phase transitions, good. It was a nice open-ended question, and I really only wanted you to say phase transitions. Right? So what would be a phase transition?
Solid to gas.
Right? We could go solid to gas. It's kind of a bit of a leap, but that works. Okay? Because we typically go through a liquid on the way through, but we could potentially go solid to gas. Okay? So that's ultimately what we're talking about for phase transitions. Our ability to interconvert between any one of those phases, okay, or between any two of those phases, sorry. Okay? What's going to dictate that ability? Okay? Well, how do I transition from a solid to a liquid? What is that represented by? Okay? Temperature, so temperature affects that. Okay? What might I report that temperature to go from a solid to a liquid? It would be our melting point, and that's being represented by a temperature. Okay? What is the temperature monitoring? Okay, heat, or more generally, energy. Okay, where is that energy coming from? So when I add heat, okay, I'm providing heat and energy to do something. What is that something it is doing? Okay, what's happening in that change of phase, though?
It's expanding the space between.
Okay, expanding the space between, okay, is a possibility, so that if I drew out a solid, we might draw it something like this. And if I draw a liquid, you would say it's something like this. I heard a couple people murmuring at that one. That looks an awful lot like going into a gas. What does it look like to transition from the solid to the liquid? It's only slightly different spacing. Okay? So there was a reference made to the transition being a change in the volume. Is the volume really changing that much when we transition from a solid to a liquid? No. Okay? And we've got physical properties to treat that for us, because we saw that when we looked back at the relationship between the mass of our particles and the volume of the particles, also known as, I think I heard someone mumble it, between mass and volume? Density. And when we look at the densities for any individual substance, we notice that between solids and liquids, there isn't a large density change. It's ultimately the same. Okay? Which means both the mass and the volumes are staying roughly the same. Okay? So we're right. There is a little bit more space in there, but it isn't significant. So when we're transitioning from the solid to the liquid, what's changing? What's allowing more movement? Or said another way, what's preventing the movement in the solid?
Attraction.
Okay, an attraction. An attraction between what?
Molecules.
The individual molecules within the compound. So when I go through and transition from a solid to a liquid, what have I done to the attraction?
Made it weaker.
Okay, I broke that attraction, or I made it weaker. Okay, name the attraction.
Molecular forces.
Okay, forces. It is typically labeled as bonds, and that is unfortunately horribly wrong. Okay? So let's go through and look at trying to label that and be careful in distinguishing those differences. If I went through and said, what is the thing holding together? I'm not going to alternate colors. That's just going to be tedious. This compound. Okay? Solid or a liquid?
Solid.
Why would you say solid?
The way you're structuring it.
Okay, the way it's nicely structured out, right? Okay. And if I went through and then heated this up, what did I break? Okay, you might say the bonds. Okay, what is the formula for the compound I've drawn?
NaCl.
Okay, so hopefully we get NaCl. Does anybody want to challenge that? No? Okay, I am. Why'd you not say Na6Cl6?
We went to the basic form.
I went down to the reduced form. Why do I need to go to the reduced form for this compound? Where is the sodium chloride compound in this formula? Anybody think they know? Nobody? You're looking at that and you're like, there's totally no sodium chloride in that.
Can be found in a few places.
There's a good answer. It can be found in a few places. Like it could be right there, couldn't it?
Mm-hmm.
Couldn't it also be there?
Mm-hmm.
Okay. If I read backwards, couldn't it be there?
Mm-hmm.
Okay. So where is the compound in that mass of stuff? It's everywhere. It's all over the place in there. There is no clean way to reference the compound in that structure. Why not? Why can't I find the compound in that structure? Okay, well, maybe it'll help if we switch to a different example. Okay, you all know what water looks like? Okay. So if I went through and drew out water, because water is a little bit more complicated, I'm not going to draw it out as many times. I might call this one my solid, and this could potentially be now the liquid. How does that representation allow me to tell that I've transitioned from the solid to the liquid? What do you have? What do you mean more uniform? The orientation of the molecules in the solid is more uniform. There's only two things, so it's kind of difficult to nail down that uniform. But you then added the important key words between the oxygen and the hydrogen. When we look at that compound, we have a partial negative, partial positive, partial negative, partial positive. In the case of the solid, what happened? The positive aligned with that negative. Okay? If I completely drew out water the same kind of way I drew out sodium chloride, would you be able to identify the compound of water in that sample? Okay, if I asked you to circle water, would you be able to do it? Anybody?
Yeah.
Yeah? Cool. Circle water.
Anywhere?
Wherever you think water is, circle. Did he just circle water? Yeah? Was there another water that he could have circled that involved those same atoms? Or any of those same atoms? Okay, I'm hearing some people shake their heads and saying, yeah, of course you could. So you could say, do something like that in purple? No, okay. So what's the other water that you could circle that involves those same atoms that he's identified in green? Can you do it? Can I take any one of the atoms that have been circled in green, so we're in that upper right-hand corner, okay? Could I do this? Okay, circle it in red. There we go. Have I circled a water molecule?
No.
They don't have a bond connecting them. So when he identified the molecule of water, we could identify the molecule of water. Could we do that for the sodium chloride? We said, no, we can't do that. Why can't we do that? What is the difference between sodium chloride and water? Sodium chloride involves a metal and a nonmetal, which would be an ionic bond. As an ionic bond, are we talking about the bond in a molecule, or are we talking about the ionic bond as in a force?
As force.
We don't really know. The ionic bond is confusing. It literally falls on the line between bonds and forces. It becomes very difficult to differentiate that. So we create an arbitrary rule system to allow us to identify the compound, so that when we write out the formula sodium chloride, we write it as the reduced ratio. When we go through and look at a compound like water, we don't do a reduced ratio. We draw it exactly as the compound is, with all the atoms that are necessary to include in it. Okay? What makes sodium chloride different from water? You've addressed what sodium chloride is. Sodium chloride is a metal and a nonmetal, which makes it a ionic bond. What's water got?
2 hydrogens and an oxygen.
2 hydrogens and an oxygen.
Covalent.
It is a covalent type bond. So in comparison between ionic versus covalent, we could use our covalent rules. Is the bond in water covalent? Okay. A brave head shake yes or no. Sorry. What is it?
A hydrogen bond?
Okay. So a suggestion, it's hydrogen bonding because there's a hydrogen present and it's bonded to the oxygen. No, hydrogen bonding is not a bond. Hydrogen bonding is on our force category. We asked, what is the bond in water? It is a polar covalent bond. Okay. When I go through and boil water, am I breaking the bonds? What happened to the bond? How do I represent a bond?
The line.
The line. What happened to the line when I boiled water?
Stays there.
It stays there. Did I break a bond? No. What happens to the bonds in a polar covalent compound? They do not break. Okay. What happens when I look at a boiling point or a melting point for sodium chloride? They do break. Okay. So right off the bat, which one's the stronger bond? Water, because what happened to the bond? It didn't break. We now have an explanation behind why polar covalent is a stronger bond than ionic bonds. Okay? And we'll get to a big misconception dealing with that in a little bit too, which is kind of fun. Okay? So then the next part, well, what is breaking when I transition from the solid to the liquid? If it's not the bond,
The force.
it's the force. So why is it important to know something about the bonds? Well, if I have an ionic bond, what kind of force is that going to generate? An ionic force. Why is that important for sodium chloride? Okay, well, how strong is an ionic force?
Strong as the ionic bond.
Okay. It's such a strong force, it's almost a bond. Okay. What is the force in the polar covalent water molecule? So what force is generated from a polar covalent bond? Dipole-dipole. If I take a green polar covalent bond, that corresponds to a green dipole-dipole force. Since I have a dipole-dipole, what should I now evaluate?
strength of the force.
Sorted to the strength of the force. I now have a dipole-dipole. Every time I get a dipole-dipole, I should make one extra step. What is that one extra step? As a hint, it's really important for water. Like, oh shit, I didn't remember that. What are the forces? Ionic, stop. When do you have an ionic force? When you have an ionic bond. What's the next force? Dipole-dipole. When do you have a dipole-dipole? When you have polar covalent compounds. Next force. London dispersion. When do you have a London dispersion force? When you have a nonpolar covalent compound. Did we just label all the forces? No! There's another sequence of words on the force side. What are those words? Hydrogen bonding. When should we decide if we have hydrogen bonding? If we have a dipole-dipole force. Have we identified that we have a dipole-dipole force in water? Yes. What's our next step?
Determine if it's hydrogen bonding.
Is it hydrogen bonding? How do I know it's hydrogen bonding?
Hydrogen bound to oxygen or fluorine or...
I would need to have hydrogen bound to oxygen, nitrogen, or fluorine. Do I have that in the case of water?
Yeah.
Yes. Okay. How do I use this information for my phase transitions? Well, the interaction I'm breaking in water is what?
Force.
Which force?
The dipole.
If I could do that funny, like rewind my voice backwards and replay.
The hydrogen bond.
The hydrogen bonding, yeah, there we go. It's hydrogen bonding that we're breaking as the force. What is the force we're breaking in sodium chloride? Ionic. Which is the stronger force? Ionic. Which is going to require more energy to break?
The ionic.
It's not like there's a chart literally on the screen that tells you which one is stronger. Okay? With these words that go increasing strength of interaction and this arrow pointing upwards. And that the hydrogen is lower on that line and the ionic is higher on that line.
I thought we said that hydrogen bonding was super strong, though.
Hydrogen bonding is a super strong thing, just like Spencer's the strongest person in this classroom. Okay? But if I throw him up against the mountain, he's going to get crushed.
So ionic bonding is the...
Okay? Hydrogen bonding is an exceptionally strong force in comparison to dipole-dipole, in comparison to London dispersion. Hydrogen bonding is not the strongest attraction because it is a force. What would be a stronger attraction than hydrogen bonding? Ionic bonds, polar covalent bonds, nonpolar covalent bonds. Okay? Have you taken a biology class out of curiosity? No. Okay. I was going to blame the biologist. Okay? And I'm right dead on blaming the biologist because they screw this one up so thoroughly when we talk about hydrogen bonding. Like, oh, hydrogen bonding is the strongest thing. No, it is not. Hydrogen bonding is not the strongest thing out there. Hydrogen bond is an exceptionally strong force. There's stronger forces called ionic. There's stronger bonds called ionic. There's stronger bonds called polar covalent. Hydrogen bonding is a strong force relative for most of our covalent compounds. What do biologists primarily care about? And even that is horribly wrong. Organic molecules, which happen to be covalent compounds. Okay? How do your muscles work? It is the pumping of sodium and potassium ions across the membrane. Sodium and potassium would be ions, making them ionic. Ionic is a stronger force than hydrogen bonding. Okay? So do not start going through and saying, well, hydrogen bonding I've learned is a strong force. It is a strong force, just like Spencer's awesomely strong. Fantastic, good job. But that doesn't make him the strongest. Okay? I don't know, are you actually strong?
No.
Okay, then never mind.
I remember that I actually did take a biology class in high school.
See? He said he admitted it. He took a biology class. The effing biologist. Okay? If you're planning on becoming a biologist, I apologize. I'm sorry. Now you won't screw it up. That's fantastic. What was the force in water? Back to the point. Hydrogen bonding. What was the force in our salt? Ionic. Which is the stronger force? Ionic. Which one's going to require more energy? Ionic. What's going to happen to the temperature at which that substance melts? It's going to go up. What's the melting point for salt? High, like 800 degrees Celsius. What is the melting point for water? Try that again.
33 degrees.
0 degrees Celsius. There's a drastic difference in those phase transitions. How could we predict that? Intermolecular forces allow us to predict that. That's pretty insanely cool. We can look at the formula for a compound, predict its force, and now compare its melting point or boiling point and predict it relative to something else. Okay? That's pretty neat. How many calculations do we have to do? None. Okay? That's really neat, because aren't you sick of conversions? Yeah, this is still a conversion. You're just not doing numbers. Okay? Arguably, you're doing unit conversions. Yeah, you like that? Yeah, no, exactly. It's the same process that we've been talking about. You have to align those pieces to see those arrangements. Okay? So let's look at some examples. Okay? We got 4 examples on here. We want to predict which of those has the higher melting point. Okay? Do these look more difficult than on the previous slide? On the previous example that we just picked? Yes, why? There's more letters. I like that. I think we can do better than more letters. So, number 1, let's fix that and get rid of some of those letters and make it easier. Okay? Should we be calling these more letters at this stage in the game? No. What should we be calling them? I'm going to argue they aren't more substances. They're more atoms. Okay? There's more bonds. Okay, we got that. Okay. Does it change our analysis?
Not really.
Okay. Brave. I would argue not at all. Okay. At least not initially. So what we need to go through and do is look at each of these and say, well, what are the bonds that are present? Why does that become a challenging question? To know that are bonds that are present, what do you need to have? You would need to have a Lewis structure. Have we done Lewis structures with compounds like this? The lab did. Okay. You're like, don't throw that at my face. I know. Okay. And yes, that is hard. So hopefully we can find an out where we don't have to go all the way into the lab to figure that out. What bonds do you see present in that first compound? And before you start going, well, literally, what is the bond present? So what bond do you see in sodium chloride? What bond is in sodium chloride? What bond do you see? You're answering too much. What bond do you see in sodium chloride? There's no other way.
Sodium and chloride.
There is a bond between sodium and chlorine. Like, that's all you wanted? Yes. Once you've identified the bond that's present, now you can answer the question about ionic. You've just internalized that. You can't internalize it for something like this because first you have to identify the bonds. So with that first structure at the left, what are the bonds that you see in that formula?
Carbon, 3 hydrogens.
Okay, so we're going to take a quick pause on that. I heard a carbon and 3 hydrogens. Please explain to me how I can get a carbon and 3 hydrogens connected with a single bond. Define a bond.
A line. Transfer of valence electrons between two atoms.
Damn. Okay. The transfer of valence electrons between 2 atoms. How do I get a bond between carbon and 3 hydrogens? You don't. Answer the question that's asked. What are the bonds that are present? There we go. I have a carbon and a hydrogen bond. I happen to have 3 of those if I wanted to look at this. You mean could I possibly go through and say, I keep forgetting about that thing underneath, 3 carbon-hydrogen bonds? Yeah. Hey, that's starting to look kind of like a structure. What other bonds do you see present? Okay, a carbon with 2 hydrogens. Did you already define a carbon with hydrogen?
Yes.
Yeah. So is that a new bond? No. Is that going to change any of my analysis? No. So should we worry about it? No. Cool. Next bond.
Hydroxide.
Okay. We're going to address a couple things here. I heard a hydroxide. What is hydroxide? Oxygen with a hydrogen is a hydroxide. Does anyone want to challenge that? You all agree oxygen with hydrogen is hydroxide. What is hydroxide? Hydroxide is a -1. And you're like, well, that's a stupid thing to add. In that bottom compound, you see that OH? That's not hydroxide. How do I know that's not hydroxide?
It's not charged.
It's not charged. How do I know it's not charged?
There's no indication on the top, right?
You might say, oh, there's nothing in the upper right-hand corner. So when I look at this compound, that compound, also not hydroxide. Can somebody name that compound for me? Sodium Wait, what?
It's not the same. It's that's an ion, whereas that's.
So when we went down here and you're like, oh, that's not hydroxide because it's not charged. That would be sodium hydroxide. Is that one charged? No, and yet what is that one? Hydroxide. So can you tell me that's not hydroxide because it's not charged? No, you've got faulty logic. Fix your logic.
It's not with somebody else.
It's not with something else. Isn't this with something else? Isn't this with something else?
The presence of hydrogen neutralizes it.
The presence of hydrogen is still there.
The other hydrogen.
So we could say an argument the presence of the hydrogen on the other side.
Yeah.
To help with that, we could draw out a Lewis structure. Is that oxygen connected to a hydrogen? No, so I don't fully accept that answer. What is the difference? Purple box with the OH in it. What do you name that? Hydroxide. Okay. If we looked at the red box, you wanted to name that hydroxide, and I said you were wrong. Damn. So what is different about the red box versus the purple box? Okay. You have to think outside the box. I didn't intend for that to come out, by the way. It just kind of worked out that way. If we look outside the box for the one we call hydroxide, what is it connected to?
A metal.
A metal, which means the connection between the sodium and the hydroxide is ionic. Because it is ionic, what do I know to be the issue with the OH? It has to be an ion. It would have to be -1, which means that species is hydroxide. What is different about the one in red? What is that oxygen now connected to? Carbon, which is A nonmetal. Because it is a nonmetal, it is not an ionic bond. Because it is not an ionic bond is the oxygen and ion. No, that's why it's called a polar covalent bond. Also known as not ionic. Okay? So when we go through and look for these things, don't just jump on, oh, OH, it must be hydroxide. Okay? That is the most common mistake to make. Okay? And with that statement, I'm going to apologize to the Tuesday lab section. Because the lab that you completed this week had you go through and qualify acids, bases, neutrals, or acid-base salt and non-electrolytes. And when you saw an OH in your formula, what did you go through and call it? A base. It's only a base if it has hydroxide. Is that hydroxide? No. So everybody in Thursday's lab, guess what? You better not get the freaking answers wrong on the lab. You now know your difference. Watch out for those definitions. Okay? So, we go back to the bonds. What bonds did you see? We heard carbon to hydrogen. We heard O to H. O to H is not hydroxide, so don't call it that. It is only hydroxide if it is an ionic compound. Okay? Are there other bonds? We do have a C to C bond. How many of you people? What do you mean by you people? Sorry. How many people saw the C to C bond from the formula? No, you didn't. Okay. One person did? Great. That's fine. You can label it a C to C. What we'll find out here is, does it matter? No. Okay. What is the bond between C to C? Good job. It is a nonpolar covalent bond. What kind of force would that generate?
London dispersion.
That would be a London dispersion force. For those of you missing those connections, guess what you need to do? Go back to Monday and review what we talked about on Monday and review that video that you were supposed to watch. Okay, which is okay. How about carbon to hydrogen? What bond is that? That is nonpolar covalent. Because we have a nonpolar covalent bond, what kind of force do we have? A London dispersion force. If we have an OH bond, what kind of bond is that? That would be a polar covalent bond. If we have a polar covalent bond, what kind of force do we have? Dipole-dipole. If we have a dipole-dipole, what should we consider?
Hydrogen bonding.
Do we have hydrogen bonding?
Yes.
Do we have a hydrogen physically bonded to oxygen, hydrogen, or oxygen, nitrogen, or fluorine? Yes. Okay. Which of those is going to dictate the melting point for this compound? Why the hydrogen bonding? It is the strongest force. Do I care about the CC? Nope. Okay. I'm not going to erase it, but we could erase it. Guess what we've done? Half of the question. Other half, what are the bonds that you see?
Carbon bonded to 3 hydrogens.
What are the bonds that you see? A carbon bonded to hydrogen. There is not a carbon bond to 3 hydrogens. That is impossible according to our definition. Okay. What other bonds do you see?
Oxygen and nitrogen.
Oxygen to what? Oxygen to sodium.
Oh, I didn't see the
Okay, just say I'm standing in front of it.
You're not.
Is that better? Should I evaluate the carbon to hydrogen?
We already know what it is.
We've already know what it is, and in fact, we already know it's in the other compound, which means
It won't have an effect on.
they won't have an effect. Do I need to evaluate the carbon to hydrogen? No. So on a test, all I have to do is immediately cross that out. I don't have to worry about it at all. Okay? For the most part. Okay, for your final, that's all, you don't have to worry about it at all. So now we have to look at the oxygen to sodium. What kind of bond is that?
That's ionic.
How do you know it is ionic?
Because it's non-metal to a metal.
Non-metal to metal, we've got it. An ionic has what force? and ionic force. Which is the stronger force, ionic or hydrogen bonding? Ionic. Which one's going to have the stronger attraction within those molecules? The ionic compound, which one has the higher melting point? The one on the right. Does anybody know the boiling points or melting points of any of those compounds? No. Are we correct? 100%. That's pretty phenomenally cool. We can predict based off of some simple structural information. Okay? That's neat to me. If you don't think it's neat, then you get to deal with all the math that you did with earlier in the semester. Okay, those are your two choices.
So, I just remember you saying that nonpolar covalent is only with carbon and hydrogen. Could it be with?
I didn't say just carbon and hydrogen. Carbon and hydrogen's the extra.
Okay,
What's the other
those
one?
have to be the same.
Same to same. So nonpolar covalent by definition is equal sharing of electrons, so they have the same electronegativities. So if I bond carbon to carbon, that's nonpolar covalent. Is fluorine the most electronegative element? Yes. What happens? What kind of bond would I have between fluorine and fluorine?
Nonpolar.
But isn't that the most electronegative element? Shouldn't that be like ionic or something?
It's the same electronegativity.
It's the same electronegativity. It's that difference that becomes the big deal.
But the ones that are the same is only carbon.
So same to same and carbon to hydrogen are nonpolar covalent.
But why is carbon to hydrogen nonpolar?
Why is carbon to hydrogen nonpolar? Because when we look at its reactivity, that's roughly where it categorizes. Okay? To get an idea on that, okay, what colors are in the rainbow?
Red, orange, yellow, green, and purple.
So it doesn't have all of the colors? There isn't like red, orange in the rainbow? Or peach? Isn't peach in the rainbow? Not one of those colors? We went through and simplified it and said red, orange, yellow, green, blue, indigo, violet. Okay? Is there a solid line that differentiates and say those are red and that's orange? No, it's a blend. The same thing's happening with our forces. Okay? And the qualifiers behind our bonds. Okay? We've created arbitrary human inventions based off of certain thresholds. The threshold for nonpolar covalent, carbon to hydrogen, and same to same. Okay? Why did we pick carbon to hydrogen and not, say, selenium to bromine? It has to do with how common it is. Carbon to hydrogen bonds are common?
Yep.
Yeah? Why are they common?
They were both in the problem we just did.
They're the most common fundamentals for life as we know it. Okay? All of our biomolecules or organic compounds are so-called organic because they are made up of carbon and hydrogen. That's why it's important, why we're told to memorize it. Because it is such an incredibly common bond, we want to be able to classify it according to these categories so that we can interpret quicker. Okay? That's why you memorize things, so that you can get things done faster, not just for the sake of memorization. Okay? What do you guys think?
Pretty cool.
Great? Cool? 3 more. Give you 30 seconds. We should start with 3. That's a good starting point. I like that. Now where do we start? Okay. I heard a suggestion for A, and I heard a suggestion for carbon to hydrogen. I'm going to guess the suggestion for carbon to hydrogen was referencing A, which is cool. I'm just going to accept that. What else do you see?
Oxygen to carbon.
Oxygen to carbon. Do you see anything else you want to evaluate? Do you see an oxygen to hydrogen in 3A? So there's an interesting question. Those pieces are all there. Is there an oxygen to hydrogen?
No.
Okay, no. What is your tip-off that you don't have that oxygen to hydrogen? It's not next to it. Okay? The oxygen is only close to that carbon. You might say that aren't these hydrogens close to that oxygen? But first, what do we have to do? Satisfy that carbon. Those hydrogens go there. Whoa, stupid
You don't have to look at
jumpy
everything
things.
that intermingles in the thing. It's just
True.
Whatever's right next to it.
It's only what's immediately next to it. And there's our structure. Okay? So there is no oxygen to hydrogen in that one. Okay? So, carbon to hydrogen. Nonpolar covalent, which would be London dispersion forces. Oxygen to carbon. Polar covalent, which would be dipole-dipole. What should we do?
See if there's a hydrogen.
Is there a hydrogen bonded to oxygen, nitrogen, or fluorine? There isn't, which means
It's just dipole-dipole.
we stop at the dipole-dipole. We move to the next one over, and what do we get?
Carbon, hydrogen?
Carbon to hydrogen. Do we need to evaluate it?
No.
No, because it was already addressed.
And then oxygen to hydrogen.
And we see an oxygen to hydrogen. Oxygen to hydrogen is?
The dipole-dipole.
Oxygen to hydrogen is?
Well, it's then a
Polar covalent, which then means dipole-dipole, which then means hydrogen bonding. Which one's the stronger force, hydrogen bonding or dipole-dipole?
hydrogen bond.
Hydrogen bonding. Which compound has the higher melting point?
B.
B. There's lots of shouting in there. Are you on board?
Can you just go over the why you go from dipole-dipole to hydrogen bonding right there?
To shift between dipole-dipole to hydrogen bonding, what you have to do is satisfy some extra conditions. Okay? Your extra conditions for hydrogen bonding, once you have a dipole-dipole, you have to have a hydrogen bonded. Helps if I spell bonded right. Bonded to fluorine, oxygen, or nitrogen. Fluorine is an exceptionally rare one to see. Why would it be exceptionally rare to look at fluorine for hydrogen bonding? How many bonds can fluorine have? Just one. So that means your compound is just HF. It's too simple of a structure, so it rarely gets tested on. Oxygen and nitrogen can have a lot more bonds, so the oxygen and nitrogen tend to get tested on a lot more frequently.
And then that's when you move over to, and it would be
Then, if that is satisfied, then yes, you move to hydrogen bonding. So in this case, we were evaluating an oxygen to hydrogen bond. That satisfies our rule for hydrogen bonding. Okay? Make sense? Okay. Next one up. Anybody want to short circuit it? B. How'd you get B? That's a big short circuit.
B's from the first one before though.
Why does it automatically have to receive the
Why does that mean it's B? Because I had B already in the first two?
No, I thought you said, what are we looking at first? And I said, B.
Oh, she wants to look at that side first.
Oh, okay, never mind.
The answer
But you can give it circle. I think it's B.
is B.
Okay, so it is B.
It's the same as before, we already did the work, so why not look at it?
Oh.
You see what I'm saying?
Oh.
Ta-da!
I've been getting smarter about deleting my work.
Oh, okay.
There we go. Are we all on agreement now?
Well, apparently I was the only one that was lost. So we've already done that work. Okay. This is going to get annoying because we've got to cross our arrows. We go through and look at that other one. What do we get?
Hydrogen.
Carbon to hydrogen.
So the non-polar covalent. Yeah, London.
Non-polar covalent. London dispersion. What's the strongest force in that compound?
Dipole-dipole.
In that compound? London dispersion force in comparison to dipole-dipole. Which one's the stronger force? Dipole-dipole, which means B. Yay? Yeah. 1. It's the same. Really? Okay, and be a little bit careful in your phrasing, but I'm going to say that again for the recording. Your suggestion was that it is B because there are more bonds to break. When we're talking about melting point and boiling point, are we breaking bonds? No. Nice adjustment. There's more forces to break. Right? What we're looking at here is the exact same strength of force, but we're looking at a different amount. Right? B has a larger structure. Because there's a larger structure, there is more opportunity for it to interact with other structures. That larger opportunity results in more interactions, which results in a higher melting point or boiling point. Okay? The analogy that I've used in the past, which is horrible, but we'll just deal with it. Okay? If I gave you the opportunity, this is only getting worse. Okay? Opportunity to be locked in this room with either a Tyrannosaurus Rex or a 2-year-old. Okay? But realize that 2-year-old is a very violent 2-year-old and was waving a knife around. Okay, you would probably take on the 2-year-old. Why? The Tyrannosaurus is really big. Okay? So if we look at that interaction, the strength of the Tyrannosaurus Rex is enough to overwhelm the strength of the 2-year-old, so we're going to favor the 2-year-old. So now let's switch that up. You're trapped in this room with 2-year-old. Again, we'll keep 2-year-old and Tyrannosaurus Rex, except now the 2-year-old, there's 50 of them. And they all have knives. We just hope they stab each other and we don't have to worry about it.
Should probably call the cops.
Okay? That starts to change the analysis, right? The amount of them, even if they're weaker, does have a different effect. So it's not just the raw strength, but it's also the amount of that strength. Another analogy that you could go through and use, right? Can you break a single piece of spaghetti, dry spaghetti? Don't be waving a floppy spaghetti at me.
Yeah.
Yes, you can break that single piece of spaghetti. Okay? But if I now ask you to break the entire package at once, that becomes a lot more difficult. Okay? The amount of that force, even if it's a weak one, can overcome a stronger force. Does that make sense? Okay? So it's not just a black and white, simple, just strength of force. We also have to look at other factors. Okay? For the sake of this class, where do you got to focus? Strength of the force. You don't need to worry about amounts. It's just raw strength of force. Okay? In the phase transitions, we're actually going to do a couple things here. Okay, heat versus temperature. If I look at temperature and I look at heat. Okay? So I stick a pot of ice on the stove and I turn on the stove. What happens to the heat?
It rises.
It starts to rise. So I would start to move on that x-axis, right? What happens to the temperature in that pot? It's also going to rise, right? Eventually, what happens? It melts. What happens to the temperature during that melting process? Okay? And that's a hard one for us to visualize because how many of you have tried boiling a pot of ice? And you laugh, probably because you've never done it. So let's flip this on its head. Okay? Let's take a liquid. We take a pot of water and I put it on the stove and I add heat to it. What happens to the temperature? It rises. It stays a liquid until eventually what happens? Okay? I hit the boiling point. So I reach 100 degrees Celsius, right? And it starts to boil. Have I stopped adding heat? No. So heat is still moving. My line still needs to move to the right. What happens to the temperature? It stays the same. Okay? It flatlines. Why is it flatlining? What is happening during that process?
You're not increasing the heat.
I am increasing the heat. That's why it's moving to the left.
Instead of using the energy for temperature change, it's using it for phase change.
Instead of the heat going in to cause the temperature to change, where's the heat going?
Phase change.
To cause the liquid to become a gas. As soon as all of the liquid has become a gas, now what happens to my temperature?
Starts to rise again.
It starts to rise again because now I'm just heating up the gas molecules. That transition, what is happening at that transition? What is the heat being used to break? Forces holding it at the liquid state. Okay? So I can correlate the energy being contributed there back to the amount of force in the structure. Okay? If I really wanted to quantify it, welcome to 151. Okay? I don't want to quantify it, so we're not going to do it. Okay? So let's look at another example here along these lines. We've got my pot of water here, liquid water. What is the formula for my water? H2O. As I heat it up, what happens?
Temperature increases.
Okay, it bubbles. We're going to talk about those bubbles in a second. Where do those bubbles go?
They rise.
Up to become
Gas.
a gas. What is the compound that is a gas? H2O. It's water vapor. What's in that bubble? It's H2O. Okay? That was water in the liquid that is turned into a gas. So what does it do? It rises out of the liquid to become the gas. Okay? You ask graduate students in chemistry. Okay? So you know where you are, barely beginning of your chemistry career. A graduate student has gone through 4 more years of chemistry. Okay? And they, oh, that.
Bro.
4 more years of awesome life in existence as a chemist. And they get asked the same question, and you know what they say is in that bubble? What do they say is happening when we boil the liquid?
Bonds are breaking.
We're breaking bonds. Is that true? No. We're breaking intermolecular forces. We're transitioning water from a liquid to water as a gas. The bubbles that we see in there are just the gas form. Okay? Why are graduate students botching that? That's an incredibly interesting question. Okay? And this will be fun to not record.